hello everyone. Am I audible? Let me check. Yeah. Hi, hello everyone. Welcome, a very warm welcome to Deeksha Vedantu YouTube channel. I hope you all are doing really great. This is our first live in 2026. I am very excited for today, and of course you know that which chapter we are going to study today. Let me just write its name very clear. It's the most weighted chapter, magnetic effects of electric current. Now, why this chapter is so important and maybe a lot discussed is because we in electricity and in light we are pretty clear that we'll get numericals from those chapters, correct? And some of the theory, and in human eye we'll definitely get 1 power of the lens numerical and some theory of the eye related defects and all. But in this chapter we can get numericals which are not completely calculation based but are hi Rohit. So we today are going to do magnetic effects of electric current. As I was telling, this chapter may require a deep understanding of concepts because there is no particular formula in this chapter. So we have to focus on the concepts primarily, and from those concepts we'll go to numericals. Our numericals will require a deep knowledge of concepts, correct? Okay, so can we start this live of the today? Okay, let's start this live with the revision of this chapter that we are going to do with the help of mind maps. Now this mind map includes, yes, so you can clearly see we have lots of information on a single page. Now this chapter, this mind map, this slide includes basic information that we need to know to start this chapter. So we have magnetic effects of electric current. The first thing we are going to study is actually magnetic field lines. But before that, what is actually a magnetic field? Ma'am, we have the basic core of this chapter is magnets. We have magnets which has North Pole and South Pole. Now the main thing about those magnets that they have a field around them. They have what? They have a field around them in which we can clearly, if I go near a magnet, not me, if I take some substance which are affected by a magnet like iron, like nickel. So if I take those substance near a magnet, they will experience a certain force, a certain attraction or repulsion. Now if I take that, if the magnet is here and my iron is 1 kilometer away, of course that the iron will not feel any attraction or repulsion, correct? But that is where magnetic field comes into the play. It says that it is a specific region or a area around the magnet in which we experience attraction or repulsion due to this magnet, correct? Now moving on to this mind map. After this magnetic field we are going to study, hi Razia, hello Malika, hello ma'am, I am just calling you ma'am. Okay, hello everyone, hello kids, a very happy new year to all of you. I hope you take a resolution that you are going to ace your boards today. Okay, so we have started the chapter magnetic effects of electric current. We saw what magnetic effect or what a magnetic field is. Now we'll be moving towards magnetic field lines. So what are magnetic field lines? Basically magnetic field lines are the imaginary lines around a magnet in which if I place a compass or a magnetic material, let's say iron fillings, they will align themselves in the form of a particular region. In that particular region they will align themselves in a particular direction in the form of lines. Those are called magnetic field lines, correct? So we have some characteristics of magnetic field lines which are very important. Ma'am, that's a very clever question, Rohit. Actually, I did not get Maggie. I ate healthy. Okay, so the characteristics of magnetic field lines are what? They are, very importantly, they are closed loops. Correct? They are closed loops and their direction is outside the magnet. They go from north to south. Inside the magnet, they go from south to north. Correct? Outside, north to south. Inside, south to north. Understood? Very basic but very important. Then they are closed loops. Then the tangent and any point on the magnetic field line. If I have a magnetic field line, say this is my magnetic field line, correct? At any point, if I draw a tangent, you all know what tangent is? We have studied in mathematics. At any single point, if I draw a tangent, then that tangent will give the direction of magnetic field at that point, correct? Then that tangent will give the direction of magnetic field at that point. This is all about magnetic field lines. Now we have magnetic field lines due to various phenomena, various magnets. This is a bare magnet we have. They travel from north to south outside the magnet, and inside the magnet they will go from south to north. Now we will study about other conductors as well, which is a straight wire and a solenoid or a circular loop as well, correct? In a moment, in actually the questions, okay? So before that, we have two very important rules for us, that is right hand thumb rule for the first, which says if I point my thumb, if I take my right hand, if I point the thumb in the direction of current, then the curling of fingers will give me the direction of magnetic field lines. Correct? Okay. And if I invert the direction of magnetic current, then the direction of magnetic field lines will change. Similarly here, the current is upward, magnetic field lines are going in. At this side, they are going inside the board. But if current is downwards, the magnetic field lines are coming outwards. Can you see? They are coming outwards. Correct? This is all about right hand thumb rule. Coming to Fleming's left hand rule. Fleming's left hand, if I take my left hand, what will happen? If the direction of magnetic field line is given, or the magnetic field is given by my index finger, the direction of current is given by current, then the thumb will give the direction of what? It will give the direction of force that is acting on a conductor placed, which is moving inside a magnetic field. Correct? How can you remember that this is force, this is magnetic field, this is current? Simply, I think you have seen this before. You can simply remember FMC, that is father, mother, child. So father will be the thumb of my hand, that is force, and mother and child will be the two fingers, that is index finger and what? My middle finger. So M is for magnetic field and C is for current. Correct? This is basic. This basic is the basic of this chapter. Correct? Now moving on to the domestic circuit, we will study about the magnetic field lines or the magnetic field around a current carrying loop, around a straight wire, around solenoid, everything. Okay. Moving to the domestic electrical circuit, we have three types of wires, that is a live wire which is positive, correct, a neutral wire which is negative, correct, and this live wire is of red color, this neutral wire is of black color, and we have one earth wire which is of green color, What this earth wire does? This earth wire takes all the excess charge from the metallic body of our appliances and pass it down to the earth. Correct? So that when we touch the metallic body of our appliances, we don't get any shock. Correct? Okay, moving on to the next. All this this is just the basic of our chapter. One topic that is left is field lines around a straight conducting wire. Oh, we have it here only. So what it says, basically we use right hand thumb rule for a straight wire as well. So if my current is going downwards, I'll point my thumb in the direction of current. Very good, in the direction of current. And if I curl my fingers, then that will give the direction of magnetic field lines around that long wire. Correct? Now, how did we saw what was the activity? They can actually ask you to explain the activity. So what we did, we take a wire and we take a cardboard, and we placed the cardboard around the wire, something like this. Okay, the wire is passing from the cardboard. Now a current is passing through the wire, and we sprinkle some iron fillings on this cardboard. Those iron fillings, when the current flows in that wire, those iron fillings will align themselves in concentric circles. Correct? In concentric circles. And that is how we see that those concentric circles is the direction of, or the representation of, magnetic field lines around a straight current carrying conductor. Correct? Okay, let's move on to the next questions. We have some little things left of this chapter, which is the unit of magnetic field is Tesla. Very important, very basic, but very important. This is the one formula that you need to remember. This formula will be used while you are doing numericals. So this formula is QVB sin theta. Q is charge on the conductor, that is in the magnetic field. This is a current carrying conductor. Okay, and V is the velocity of that conductor, because it's moving inside the magnetic field, and this is the magnitude of that magnetic field. Now one more formula comes out of this, that is ILB sin theta, that is current on the conductor, length of that conductor, and again magnetic field. Theta, however, is the angle between the velocity vector and the direction of magnetic field, and here theta is the angle between length of that conductor and the magnetic field. Correct? So some small chit-chat points, which is for a circular loop. Now I told you we'll study about the circular loop. This is my circular loop, and this is then connected to a battery and all. If the current is what? If the current is clockwise, for anti-clockwise right now, for anti-clockwise inside the loop, for anti-clockwise, the magnetic field is outwards. Here the magnetic field is outwards. But if my current is clockwise, if the current is clockwise, this is clockwise and this is current. If the current is clockwise, then the magnetic field will be inwards inside the loop. This is very important, because outside, if it's going in, then it will be coming out from outside the loop. Correct? Understood? Okay, this is the basic, and we have, yes, a very important slide, that is factors affecting the magnetic field. Now magnetic field, this is due to the current carrying conductor that is placed inside a magnetic field, that magnetic field which is passing through that conductor. So around the magnetic field generated around the conductor when a current is passing through that conductor. Understood? So it is directly proportional to the current, okay, inversely proportional to the radius of the loop in case of circular loop. If the radius is bigger, magnetic field will be less. Radius is less, magnetic field will be more. Then distance from the conductor, distance is more, it's inversely proportional. Distance is more, then magnetic field will be less. Distance is less, magnetic field will be more. And in case of solenoid, number of turns, more the number of turns of that insulated copper wire of the solenoid, that means more the current, more the strength of magnetic field generated. Correct? Can we move to the next? Okay, let's move on to the topic which is why we have come here, that is the questions. A very important thing. Questions are very important for this chapter because they will include both conceptual as well as a little bit of numerical questions. Okay, let's read it. Draw the magnetic field lines of a bar magnet. The magnetic field lines are closed curves. Why? So we have two questions in a single question. Okay, so first we need to draw the magnetic field lines of a bar magnet. Now this is very simple, correct? This is very simple. We'll get a bar magnet, and if you can let me know in the chat. I have told you multiple times the direction of magnetic field lines. Will it be north to south, outside the bar magnet, or inside the bar magnet? I know the magnetic field lines will form a closed loop, correct? Now will they form the loop, will they go from north to south outside the magnet or inside the magnet? So ma'am, this is just a faltu ka question. We know that outside the magnet the field lines go from north to south, and since those are closed loops, they go from south to north, outside, north to south. Same, they go from north to south outside the magnet and south to north inside the magnet, and there will be multiple field lines and they all will be closed, correct? They all will be forming closed loops, and they will not intersect each other, correct? They will not intersect each other. No two magnetic field lines can intersect each other, correct? Now they are asking, the magnetic field lines are closed curves, we know, but why? This is just a basic explanation for this, is that we know magnetic monopoles does not exist. A single north pole and a single south pole, just like positive charge and negative charge, they do not exist. Magnetic monopoles does not exist. In case of charges, we know that plus Q charge, if I have, the field lines, the electric field lines will go outwards, correct? But in case of magnets, single north does not exist. No, these poles always exist dual, correct? Wherever there is a north pole, there will be a south pole there. So my magnetic field lines go from north to south, but they also go back from south to north. As in case of dipoles, we know, correct? These travel from positive to negative, but they exist, single charges do exist. That's why the field lines can break or they can stop at some time, but magnetic monopoles does not exist, and hence the magnetic field lines are closed loops, correct? Okay. Second question says, this is an MCQ now. The second question says, a compass near a solenoid. We have a solenoid and a compass. If we brought a compass near it, it will show a deflection due to which of these reasons? Electric field, heat, magnetic field, or resistance. Let me know the answers. Why the compass needle will show a deflection when we bring it near a solenoid? You know the poles of solenoid, right? If I have on the positive side of the battery, a south pole will be created, or negative side of the battery, north pole will be created, negative north. You can remember like this, right? Negative north. So on the negative side of the battery, north pole will be created. Now again, This is a very easy question, but it is an PYQ. Okay, so we just know that compass, when a current flows inside a solenoid, a magnetic field is generated around it, and due to this magnetic field, my compass needle will definitely show a deflection. Correct? Okay. Third question says, two parallel conductors. Now, very important question. Two parallel conductors carrying current in the same direction. There are two current carrying conductors. They are carrying the current in the same direction. Both have, let's say, current in the upward direction. Now, will they attract? Will they repel? Will they remain stationary? Or will they start to rotate? Let me know the answers if you know. Will they be stationary? Will they rotate, attract, or repel? The current in both these parallel conductors is in same direction. Okay, so in case of, always remember, these are not charges, these are current in parallel conductors. So always when the current in both these parallel conductors, when the current is in same direction, they will attract. When the current is in same direction, these two conductors, they will attract, they will start to come towards each other, and when the current is in opposite direction, they will start to repel. Correct? If the current is in same direction, they will attract. If the current is in opposite direction, they will repel. Correct? So in here we have same direction. That means the answer is A. That is, they will attract towards each other. Okay? Okay. Fourth question says, which of these factors has no effect on magnetic field? Which of these factors, read the question very carefully, which of these factors has no effect on the magnetic field? Current, distance, resistance, or the core material? Let me know in the chat what do you think will not affect the magnetic field? Just a minute. Now, factors are very important. The factors on which magnetic field depends, these are very important. That's why I had a proper slide dedicated to it. Correct? I have a proper slide dedicated to it. And which of these factors does not affect the magnetic field? So ma'am, current definitely affect the magnetic field. So current is not the answer. Distance also definitely affects magnetic field. It is inversely proportional to the strength of magnetic field. Current is directly proportional to the strength of magnetic field. Resistance, however, is questionable. Core material, when we put an iron core inside a solenoid, let's say, it does affect the magnetic field. So this is also not the answer. So the answer will be resistance. The resistance of wire, let's say, that we are using, or resistance of the current in the conductor, that will not affect the magnetic field. Correct? Okay. Fifth question, moving on to the fifth question. A big question, you have to read it carefully now. For a current in a long straight solenoid, we have a solenoid, north and south poles are created at the two ends, that we know. Among the following statements, the incorrect statement is which one? A. The field lines inside the solenoid are in the form of straight lines, which indicates that the magnetic field is same at all points, but it's inside the solenoid. They're talking about inside the solenoid. Correct. Second option we have the strong magnetic field produced inside the solenoid can be said to magnetize a piece of magnetic material like soft iron when placed inside the coil. Okay, that we have also studied. The pattern of magnetic field associated with the solenoid is different from the pattern of the magnetic field around a bar magnet. Okay, let me see this one. Now this is my solenoid, correct, and the kind of magnetic field lines that are produced in it will be what? We know they will be, we know that much that they are closed loops, but we know they are something like this, and this resembles what? And they go from north to south outside, south to north inside, north to south outside, south to north inside. This resembles the magnetic field lines due to what? Due to bar magnet. So this one actually is the correct answer, because they have asked us the incorrect statement and they have said this different, the solenoid is different from the pattern of magnetic field around the bar magnet. Correct? Okay. Sixth question, it says the force experienced by a current carrying conductor placed in a magnetic field is the largest when the angle between the conductor and the magnetic field is what? Let me know which the force, when the force experienced by a current carrying conductor and that conductor is placed in a magnetic field. Now the force experienced by that conductor is due to that magnetic field is largest when the angle between the conductor and the magnetic field is what? Let's say this is my conductor, okay, and this is the magnetic field. Now there can be two chances. My conductor can be like this, correct, and this is the magnetic field, or my conductor can be at an angle somewhere and the magnetic field can be like this. Magnetic field is like this. So in which case the force will be the largest. Now I told you one formula in the starting that you need to remember, correct? That was F equals to QVB sine theta, correct? Now this theta is of sine, correct? This is sine theta. So sine theta, this whole force will be maximum when sine theta is maximum, and the maximum value of sine theta is what? It is 1. At what angle the sine theta value is 1? That is 90 degree, ma'am. Correct? So the correct case will be this one, that my conductor, the angle between the conductor and the magnetic field is 90 degrees, correct? So 90 degrees is the correct answer. Moving on to the, before moving on to the next question, I want you to join this WhatsApp channel. Will get you all the updates, all the notifications on this channel only, okay? So make sure you join this WhatsApp channel so that you don't miss any updates, that we are bringing so many videos, so many lives for you guys, okay? Okay. Seventh question, it says, let's read it again very carefully. The question says, on what factors does the force experienced by a current carrying conductor placed in a uniform magnetic field depends? No. On what factors? Again, we have studied this, the factors on which the current carrying conductor, the factors on which the force experienced by a current carrying conductor depends. Now this is a question again from that formula. So we have QVB, correct, sine theta. Now if a conductor is placed inside a magnetic field, yes. Now if a conductor is placed inside a magnetic field, when the current that is passing through the conductor can affect the current, because the formula was also ILB sine theta, correct? Now what else? Of course magnetic field will affect, the force that is being experienced by that conductor, right? And length of the conductor will definitely affect the force that is being experienced by it due to that magnetic field, correct? And velocity of that conductor inside the magnetic field, correct? What else is left? Angle. The angle at which it is placed inside the magnetic field, if it is parallel to the magnetic field, if it is perpendicular to the magnetic field, or it is at a certain angle. So all this will be different. All those orientations will give a different force due to that magnetic field, correct? Okay. Eighth question, a very important question, a very repeated question, if you can see. Next, it can come in 2026 now. Okay, a uniform magnetic field is directed vertically upwards. Now, we have a uniform magnetic field that is directed upwards, correct? In which direction in this field should an alpha particle, which is a positively charged particle, in which direction should an alpha particle be placed or be projected so that it is deflected southwards? Now we need directions. Now for this you should know what where is north and south. So obviously north and south are upwards and downwards. On the right side of north we have east, and on the left side of north we have west, correct? Now if you draw this on your paper, if you draw this on a paper, so this is my magnetic field, correct? Something like this. Nowhere this stylus is visible. This pen is my magnetic field, correct? Now it's visible, yes. So this is magnetic field which is coming upwards, which is in a vertically upward direction. Now this is north, south, east and west, correct? Upwards is north, south, east and west. Now they are saying that in which direction this alpha particle should be projected so that it experiences a force and it goes towards, it is deflected towards south. So south is my this part. Now for this we are going to use Fleming left hand rule, correct? Because we need to find the force that should be applied on this alpha particle, correct? So if the direction, magnetic field direction is upwards, correct? This is upwards. The current will be in the same direction as of that alpha particle because alpha particle is charged. So current will be in south direction. So my magnetic field is upwards. If you draw in the plane of paper, the upwards will actually outwards, correct? Like this, but in the plane of board it will be like this. So this is my magnetic field, current is southwards, correct? This is south. So this force, where will it be? It is in the direction of west, correct? Magnetic field outwards, current in the south, so force will be in the west direction. So west is the answer for this particular question. These are the questions I was talking about when I was telling you that you need to be conceptually strong, not just numericals for this chapter. And they have asked, name the rule you have used to find the direction. So that is Fleming's left hand rule, correct? This is Fleming left hand rule. What did I type? Okay. Can we move to the next question? Okay, the next question, it says, 9th question. We are already on the 9th question. Can a freely suspended current carrying solenoid, we have a freely suspended current carrying solenoid, okay, in the air. Now they are asking, what will happen when the direction of current, so they are asking what will happen if I suspend from a wire a current carrying solenoid. Do you know what will happen? Will it stay fixed? Will it align itself in a particular direction? Will it start to rotate? What will happen? If you know, let me know in the live chat or the comment section, wherever you love. Now, it won't stay still, that much we know, correct? Why? Because it's a magnet. There are south pole and north poles that are getting created on these magnet, on this solenoid, correct? And we know that earth has a certain magnetic field, and if I have a compass needle, let's say, I know that compass needle is also a freely suspended magnet, right? Nothing is holding it. So that current carrying that needle, that compass needle, is almost resembled to this solenoid, freely suspended solenoid, because this is also a magnet now. And since it is suspended with a rope, it will align itself in the direction of magnetic field, correct? It will align in the direction of whose magnetic field? In the direction of Earth's magnetic field, correct? Earth's magnetic field. North will point towards magnetic north of Earth, and south will point towards magnetic south of the Earth, correct? Now they are asking what will happen if we change the direction of current in the solenoid. If the direction of current in the solenoid is reversed, nothing, ma'am. If this is current upwards and this is going up, let's say, okay, if the direction is reversed, we know that polarity of this solenoid, the north pole and south pole will switch, correct? And if north pole and south pole will switch, that means that the magnet is inverted now, and if it was pointing like this, it will point like this, because north was here first. So north go backwards, it will again align itself in the direction of Earth's magnetic field, so the solenoid will rotate kind of 180 degree, correct? Can you move to the next question? Okay, 10th question says, if the direction of current in a solenoid when viewed from a particular end is anti-clockwise. We have a solenoid again, and the direction of current is anti-clockwise, then this particular end of solenoid will be what? North, south, east or west pole. Hi Pankaj. So Pankaj, can you let me know the answer of this question? If we have a solenoid and it is viewed from a particular end where the direction of current is anti-clockwise, so which will be this pole? So this pole, we know that if current is anti-clockwise, that pole will always be north pole, correct? And if the current is in clockwise direction, that pole will always be south pole. So the correct option in here, they have asked us anti-clockwise, so that is north pole, correct? Okay, moving on to the next question, 11th. No, the answer is actually A, that is north pole. In case of anti-clockwise, you will get north pole on that particular end. North pole, it's north pole, Pankaj. For anti-clockwise, A, this one, north pole. Okay, I can see why you're getting confused. Correct now? The answer is north pole for anti-clockwise current. Okay, next question, it says assertion reason question. These are also very important. Assertion says two magnetic field lines around a current carrying straight wire do not intersect each other. Okay, this makes sense. And the reason is the magnitude of the magnetic field produced at a given point increases as the current through the wire increases. This is also true. Then which will be the answer? Can you let me know? What can be the answer of this particular question? Both are correct, both are not correct, they are correct explanation or they are not. Let me know in the live chat. So when you are talking about magnetic field lines, we know they can't intersect each other. So assertion is definitely correct. And we know that among one of the factors affecting the magnetic field strength or magnetic field lines, we know that as the current increases, the strength of magnetic field lines increases. Correct? And so R is also correct. But are they correct explanation? Is the reason correct explanation of assertion? That is where we have to see. This does not intersect each other. That has nothing to do with is the current more, is the current less. Correct? So the answer is actually B, that both assertion and reason are true, but reason is not the correct explanation of assertion A, because here the correct explanation is that if two magnetic field lines intersect each other, then at that point we'll get a tangent in two different directions, and that is not possible. Correct? Okay, moving on to the next question, that is 12th. And it asks, an induced current is produced when a magnet is moved inside a coil. Coil is generally, we talk about solenoid. So we say that we have a magnet which is moved inside, there is a magnet and we move it inside the coil. The magnitude of induced current does not depend on what? The speed with which the magnet is moved, the number of turns of the coil, the resistivity of the wire of the coil, or the strength of the magnet. Okay, Pankaj is saying B. B is the number of turns of the coil, are you saying? Actually, one of the very main factors on which the current depends, the magnetic field depends, is the number of turns of this solenoid or coil. Well, actually is number of turns per unit length, but in till your class, till 10th class, we can say that number of turns is a very important formula. More the number of turns, more will be the current flowing through that coil, and as the current increases, we definitely know magnetic field increases. Correct? So see, let's see from this formula, QVB sine theta, this is the force that is happening on that conductor due to the magnetic field. Correct? Now this depends on speed. Definitely, if the speed is more, the magnetic field experienced by it will be more. Then the number of turns we know is very important. Correct? So the current that is being induced on this is definitely depends on the speed with which the magnet is moving. It definitely depends on the number of turns of the coil, and it definitely depends on the strength of the magnet. More powerful a magnet is, more current it will induce, right? And hence our answer is C option, that is resistivity of the wire. Resistivity of the wire will not affect the magnitude of the induced current. Correct? Okay. 13th question, it says, now this is a very, very, very important question. I have done this before, this question in almost all my lives. Why? Because this is very important. Yes, it's fine, Pankaj. We are actually asking on which it does not depend. Okay? Read this question carefully and let me know if you know the answer. State the rule used to find the force acting on a current carrying conductor placed in a magnetic field. Which is the rule that we use to find force? What are you writing? Okay, so in here we need to know the rule that is used to find a force. Now whenever we need to find a force, I have remembered it like this. Okay? From force, F for force, that is F for Fleming's left hand rule. Correct? It's just simple. If you need to find force with the help of a rule, we just have two rules, Fleming left hand rule or right hand thumb rule. Okay, Yoga is asking, ma'am, what is solenoid? So solenoid is, we take a wire of a insulated copper wire. So when insulated copper wire is turned around in multiple turns, correct? Okay, are we back now? Yeah, I'm sorry, there was some technical issue, I guess. Okay, so maybe you didn't hear me explaining a solenoid. Solenoid is nothing but a insulated copper wire wrapped in a number of turns around air core, we say. That is a solenoid, and if you wrap that insulated copper wire around a iron core, that becomes an electromagnet, which is being used in different kinds of applications. Okay, that is simply a solenoid. Now moving back to this question, so from force we identified that this is a Fleming left hand rule. The question they are asking is given below are three diagrams showing entry of an electron. So this is an entry of an electron in a magnetic field. This is my magnetic field, this is electron. This is electron, magnetic field. Now they are asking identify the case in which the force will be maximum and minimum respectively. Correct? So in out of all these three cases, in which case the force on the electron that is entering into the magnetic field is maximum. Okay, so a very important formula that I told you to remember was what? That is QVB sine theta. Correct? Now electron is moving inside a magnetic field with an angle of what? 0 degree here. Correct? In here angle is a general angle, maybe 30, 60, anything we are not given. In this first case, the angle is actually what? It is 90 degrees, we can clearly see. Correct? And they are asking in which case the force will be maximum. Now for maximum force, the theta should be maximum, sine theta should be maximum, and sine theta is maximum value of sine theta is 1 at an angle of what? At an angle of 90 degrees. Correct? So for maximum, the maximum force will be in the first part. Correct? Now minimum means sine theta minimum value is 0. Correct? Which is at an angle of 0 degree or 180 degrees. Correct? So in this question we don't have 180 degrees, we just have 0 degrees. That means for minimum force, electron should travel parallel to the direction of magnetic field or in the direction of magnetic field. Correct? So for maximum first case, for minimum third case, and in between them we will get some value of force for this second part. Correct? Okay, 14th question, again a very good question. The resultant magnetic field at point P, the resultant magnetic field at the point P situated midway between two parallel wires placed horizontally, each carrying a steady current I is. So in both these wires the current is in the same direction. Now we need to see the resultant magnetic field at this point P. Will it be vertically upward direction? Will it be in the same direction as the current in the wire? Will it be 0 or will it be in the vertically downward direction? Okay, so okay, hi Manya, good evening, welcome to the live, and can you let me know the answer of this question? what will be the direction of magnetic field, or the resultant magnetic field at point P due to these two parallel wires, due to the current flowing in these two parallel wires. Yeah, okay. So when we have parallel wires and current is moving through them, so what is happening? We are getting magnetic field lines are getting generated around these wires. That is being found by what? Right hand thumb rule. Now I will point my thumb in the direction of magnetic field lines, that is in here, in the direction of current, sorry. So this is the direction of current, and from here at point P the magnetic field lines are going in, correct? They are going inside, correct? And let's say they have a magnitude of m, correct? In here, due to the above wire, the magnetic field lines are going in, but at point P they are coming out. They are coming out. Now, since the point is equidistant from both wires, the magnitude of this field is also m. So at one single point, magnetic field is going in and it's coming out, and the magnitude is same. So what will happen? The resultant magnetic field will be what? It will definitely be 0, correct? Because these are in opposite directions with same magnitude, correct? Okay, moving on to the last question of this live, we have a very important question. The question is 15th. Draw the pattern of magnetic field lines of a current carrying solenoid and a bar magnet. Now just let me know if we will have the same kind of magnetic field lines for these two or different kind of magnetic field lines for these two. Let me know in the chat. Okay, so in case of both these, we know solenoid behaves like a bar magnet. So this is my bar magnet, this is north, this is south. This is, however, my solenoid. This will be north and this will be south. For both the cases, the magnetic field lines will be in the form of circular loops, that is something like this, and they should not intersect each other. Outside the direction will be north to south, inside it will be south to north, correct? And in case of solenoid as well, we have similar kind of magnetic field lines. The outside they travel from north to south, inside they travel from south to north, correct? So for both solenoid as well as for magnet, for bar magnet, the magnetic field lines are same, correct? Representation of magnetic field lines are same. Second is, list one distinguished feature between the two fields. The field due to bar magnet and a field due to the solenoid. Now this, well, you let me know, I don't know. Okay, so in two distinguished features between these two fields are the field due to bar magnet and solenoid, correct? Now this is a very important question that you should remember. It has high chances of coming in the paper, correct? Now in case of bar magnet, it is a permanent magnetic field, correct? The magnetic field is permanent. However, in the case of solenoid, if I close the key, if I open the key, there is a key, correct? We need to close it for the current to flow. If I open the key, current will stop flowing. As the current stops flowing, this magnetic field will vanish, correct? So this is a temporary magnetic field. This is a temporary magnetic field. Second, however, they asked one, you can't change the polarity of magnetic field in this case, can't change the polarity of magnet or magnetic field that has been produced due to our magnet. But in case of solenoid, if I switch the terminals of battery, now if it in this side this is negative, if I put positive in this side, something like this, the polarity of the direction of current will change and the polarity of magnetic field will change around the solenoid. Polarity of magnetic field can change. Correct? And this is also known as, if you insert an iron core, this is also known as an electromagnet. So which is a temporary magnet. Correct? Okay, that was it for today's class. We have done 15 most important, most expected questions from the chapter magnetic effects of electric current, and we have done all these questions for the light as well as electricity chapter as well. You can go watch them, and I hope you liked all the questions, and I hope they will definitely help you in your boards as they are coming very near. Your boards are very near, so do not worry for physics. I know a lot of you might fear physics, but it's a really wonderful, it's a really lovely subject. If you just give it some time, if you try to solve the questions, it will really give a fruitful output for you. Correct? So next live I'll be coming live on Monday as well with the next chapter, that is human eye. We'll be doing defects, we'll be doing lots of diagrams, how to correct those defects, and all the questions and all the numericals that can come from the chapter. If you have any doubt, you can ask, or till then, till the next live, tata bye bye. If you have any doubt after, you can comment down in the comment section, and you should definitely join our WhatsApp channel because we are coming live every day, twice, in the morning as well as in the evening. So you can go watch those lives. We have covered all the syllabus of all the subjects on Deeksha Vedantu channel. So go join this channel so you don't miss any notifications of our new lives, of our new lectures, and subscribe the channel and like this video. Okay, bye bye.